This is the continuation of Chapter 6 notes. Last time we talked about work and kinetic energy, and we said kinetic energy is the energy of motion. Today we're going to focus a little bit more on potential energy and the different forms. So potential energy is an energy associated with the position or configuration of an object and its surroundings or other objects in the system. It can be thought of as a stored energy. There's several different forms of potential energy. Probably the most common one is gravitational potential energy. Another one we will see this unit is elastic potential energy. There's also electrical, which we'll see next semester, chemical, which we won't deal with, and some others as well. So gravitational potential energy, probably the most common form of potential energy. It's an energy associated with the object and the Earth. Both must be part of this system. And we can calculate gravitational potential energy as mass times our acceleration due to gravity times y, where y is our height. The textbook, I think, just uses GPE in the equation itself. The AP equation sheet uses a capital U for all potential energies, along with some subscript to describe which type of potential energy we're talking about. Any change in gravitational potential energy is going to be the result of some external work, or it could be, the object's kinetic energy being converted into gravitational potential energy. So, for example, a ball rolling up a hill, it would lose kinetic energy and it would gain this gravitational potential energy in that process. So, just as I was saying, GPE and KE can go back and forth in quite a few different scenarios. So one example here is, this pendulum, where the pendulum bob is kind of moving up and down as it swings back and forth. Again, the potential energy is not just of the pendulum itself, it's a potential energy of the pendulum and Earth system. And one thing really with all of our forms of energy, but especially important with gravitational potential energy, is you get to set the reference height, right? So this is similar to motion, right? You get to set what zero velocity really means. So this is true as well for kinetic energy, but it just comes up much more in gravitational potential energy problems. You should consider where is the best spot to set y equals 0 to, and typically you want to do that at the lowest height. So for a pendulum, you wouldn't set y equals 0 at the ground. You'd set it at that lowest point. So right when the pendulum's hanging straight down, you'd say that's probably where y equals 0. And that can just simplify the problem solving steps. All right, so we have our first example. Go ahead and pause and resume when you're ready. So for A, we're trying to find the gravitational potential energy at points 2 and 3 if we set y1 equal to 0. So we're starting at our reference height here. So you should get the gravitational potential energy at point 2 as 98,000 joules. And the gravitational potential energy at point 3 as negative 147,000 joules. It's a little weird to think of having a negative, but really a potential energy in and of itself doesn't really mean anything. It's really just changes in potential energy that actually have physical meaning for us. For B, what is the change in GPE when the car goes from point 2 to point 3? We can just subtract. So final minus initial, we end up with negative 2.45 times 10 to the 5th joules. And for part C, do your answers to A and B change if you set y3 equal to 0? So if we change our reference height, what impact does that have on our answers? Well, it would change our answers to part A, but the key is it does not affect our answer to part B. So the change in gravitational potential energy from point 2 to point 3 is the same regardless of where we set our reference height. And that's important, right? Because really it's that change that matters. So that change should be constant regardless of where we decide to set y equals 0 to. There's a separate equation to calculate gravitational potential energy out in space. And that's because we can't really use, mass times gravity times our height if gravity is not constant, if it's not, staying at 9.8. So we have to use a different equation. And you may see in this equation and say it looks a little familiar because it's very close to Newton's universal law of gravitation. So we have gravitational potential energy equals the negative of our gravitational constant times each mass divided by r. So really the only difference is that negative sign, and instead of r squared, this equation is just r. So again, this is only used for, maybe the sun and the earth. You could figure out how much gravitational potential energy they have at some position. You would only use this for objects out in space. And again, it's a little weird to have that negative sign, but that negative sign is necessary so that whenever there's a change in gravitational potential energy, that's really what matters. So if it's increasing or decreasing, that will tell us what's happening, in this case, to the kinetic energy. The College Board places a really strong emphasis of understanding the difference between looking at an object and looking at a system, especially when we're talking about potential energy and specifically gravitational potential energy. So just for example, an object that's on a ramp or some distance up in the air, if we're just talking about the object, it has no gravitational potential energy, none. If it's just at rest, it has no energy whatsoever, right? No kinetic, no gravitational potential. If we are looking at a system containing that same object and Earth, then it does have, that system does have gravitational potential energy. If we are including the Earth as part of our system, then as the object falls, the energy of our system is converted from gravitational potential into kinetic. And we can say mechanical energy is conserved. We'll talk a little bit more about what that means. If we are not including the Earth as part of the system, then we would have to include gravity as an external force. So when gravity acts on our object, we can think of it as an external force or a net force. And we can say, the amount of force times the displacement equals the amount of work done, and that work done results in a change in kinetic energy. So typically it's easier to use conservation of energy to say our gravitational potential is just turning into kinetic. But if you don't include the Earth, then you're going to have to treat it as an external force that's doing work on the system. You still get the exact same resulting kinetic energy, but it's just harder. Another common form of potential energy for this semester is elastic potential energy. So typically we're looking at like a spring that can stretch or expand, maybe a rubber band. The change in potential energy is equal to the work done to compress or stretch that spring. And once you've, for example, compressed the spring, that potential energy that's stored in the spring can be returned back as a different form of energy, in this case kinetic energy, as it launches the ball. The force required to compress the string relates to the stiffness of the spring and how much you're compressing it. So the more you compress it, the harder it is to continue to compress it more. And it also depends on the properties of the spring. That's what we are referring to here when we say the stiffness. If you were to pull the spring to stretch it out to the right, so shown here in part B of this diagram, the spring is going to try to pull back in the opposite direction. And this leads us to what's known as Hooke's law, that the force that the spring is exerting is equal to negative K, where K is our spring constant. Again, that's related to the stiffness of the spring, times X. And X is how much the spring is stretched or compressed. You can think of it as the displacement of the spring. So if you're stretching it to the right, the force from the spring will be to the left. That's why there's the negative sign there. Honestly, often when we're using this expression, we're going to use it with our, F equals ma equation. And so you don't necessarily use the negative sign. You have to think about what direction you're setting as positive and negative, and then just go with that kind of sign convention. So when you're stretching a spring, the force that the spring exerts, or the force that you use to stretch it, varies over time, right? If we look at Hooke's law, the force is proportional to the amount of stretch. So as you stretch it more, the force increases linearly, as we can see in this graph. So to stretch it some amount, that final amount, it would require some maximum amount of force. If we want to know the average force, we could just take, half of that maximum amount. So you can see that with the dashed line here, that horizontal dashed line. For work, if we do that average force times the displacement, we can figure out the work. Remember, work is the area under the curve. You could also think of this as, 1/2 base times height, where the height is kx. So 1/2 times our base, which is x, times height, kx. Either way, you get the same equation. So the work done is 1/2 kx squared. In other words, the stored elastic or spring energy, they use S for spring here, but really this is like any sort of elastic potential energy. It's equal to 1/2 kx squared. So looks pretty similar to our kinetic energy, 1/2 mv squared. Just keep in mind x is the stretch or compression of the spring. It's not the actual length. And k, again, is what we call a spring constant. It depends on the properties of the spring. All right, here we have our first example with elastic potential energy. Pause and resume when you're ready. All right, so first I've just written out that we have our force of the spring and the force of gravity. Since they're acting in opposite directions, I put that negative sign there. But the magnitudes are the same, which is really the more important part. I can substitute in my expressions for both the force that the spring is exerting and the force of gravity. I can plug in values that are given. So it tells us the spring constant, 53 newtons per meter. So there we have our units with the spring constant, newtons per meter. X, we don't know that quite yet. For the mass, we have 2.5 kilograms, gravity 9.8 meters per second squared. We end up solving and getting x as 0.46 meters or 46 centimeters. We're not quite there, to our answer yet. So it said the end of the spring is next to the 15 centimeter mark of the ruler. So we're assuming this spring is, 15 centimeters long. 46 centimeters is how much it stretches. So I need to take 15 centimeters, add 46 centimeters, and that will tell me where that mass will line up when it's fully stretched. All right, so when we're talking about energy, you will hear these the terms conservative forces versus non-conservative forces. So we'll talk mostly about conservative forces today. So a conservative force is any force where the work done by that force is available to be converted back into other forms of energy. So for example, when a ball rolls up a hill, the gravitational potential energy it's gaining will be able to be turned back into kinetic energy later. Probably the easier way to think of conservative forces, or to figure out if something is conservative or not, is to see if it matches up with one of our forms of potential energy. So, for example, gravitational potential energy, that means the force of gravity is a conservative force. So when gravity pushes an object down, it's probably turning into, kinetic energy. Elastic is another conservative force. Electrostatic forces are also conservative. We won't really talk about that until next semester. Another way of thinking about conservative forces is that the path that the object takes does not matter. So the amount of work done, for example, by gravity, if you carry a backpack up a ramp versus if you just step straight up onto some ledge, the work done by gravity is the same either way. It doesn't matter. Friction, on the other hand, is an example of a non-conservative force, where if you take a longer route, friction is going to end up doing more work in the process, right? Because you're having to move a greater distance that way, and friction will continue to act as you move that greater distance. So if we only have conservative forces, then the total mechanical energy of a system is conserved. So mechanical energy includes any kinetic energy as well as any potential energies of our system. So again, keep in mind we have to be looking at the system containing all of the objects involved with our potential energies in order for there to be that potential energy. If we just have these conservative forces, that means mechanical energy is conserved. Generally, this is not true if there's friction, and it's not true if there's any applied force. So if there's like someone physically pushing these objects, then mechanical energy is not conserved. And if there's friction, mechanical energy is not conserved. For us, our main forms of energy that we will use with calculations this semester are kinetic, gravitational potential, and elastic potential energies. So if we combine all three, that's kind of like the max forms of energy we'll have to deal with. All right, here we have our next example problem. Pause and resume when you're ready. Okay, so for part A, we're trying to find the spring constant of this bungee cord. So that 31 meters, because the unstretched length was 12 meters, that means it stretched 19 meters. So I've just gone ahead and labeled that X, which is our spring stretch, is 19 meters. So with this bungee jumper, you might think, okay, there's, at some point they're moving, at some point they're changing height, and at some point we have a bungee cord that's stretching. So there's kind of all three forms of energy associated with this scenario. Luckily, as we'll see, a lot of these forms actually are just zero at the points we are looking at. So really, if we choose strategically, the most logical places to look would be before the bungee jumper jumps and after she's reached that lowest point, right? Once she's fallen 31 meters. So my initial kinetic energy is 0. For the initial gravitational potential energy, I'm going to use a height of 31 meters so that after she's fallen 31 meters, gravity or GPE is 0. Right? So I'm strategically using that lowest point as y equals 0. So really there's only one point where she does have GPE. The bungee cord is not stretched initially, so 1/2 kx1 squared is also 0. At the lowest point, right, once she's reached the lowest point, she's not moving down anymore. She hasn't yet started coming back up, so kinetic energy is 0 there as well. Very nice. Kinetic energy is not 0 everywhere in between those 2 points, but at our two extremes, we have Ke being 0. 0 GPE as well, and at the very bottom, the only type of energy we're looking at is elastic. And again, the stretch is that 19 meters. So luckily that simplified pretty significantly in that first line, so we can go ahead and solve for K, and we get about 104 newtons per meter for our spring constant. For part B, we're trying to find acceleration. With acceleration, we really need to look at forces, and so the maximum acceleration is going to occur where we have our maximum force, and the maximum of force occurs where we have our maximum stretch. Remember Hooke's law that F equals negative kx, so the more it stretches, the more force we have. Before it stretches, the only force we have is gravity. So if this is less than the force of gravity, then maybe our max acceleration would just be at 9.8, but that's not going to happen. All right, so we have Newton's second law. Our net force equals mass times acceleration. At that bottom point, there are two forces acting on our bungee jumper. There's our bungee cord pulling our bungee jumper up, and gravity pulling our bungee jumper down. We can set that equal to mass times acceleration. I know the spring constant and the stretch. I know mass and the acceleration due to gravity, and so I can use that to solve for A, and we get our acceleration is 22.2 meters per second squared. So that is quite a bit larger than the acceleration due to gravity when she's falling. And that makes sense. If she's falling for any amount of time, then the acceleration at the bottom should be greater than that acceleration that she has while she's falling. For our next example problem, this one's a little tricky, so pause, try it out, and resume when you're ready to see the answer. So this problem is a little unique in that we aren't given any values. The closest we get to a value is that we don't want the passengers to undergo an acceleration of more than 5g, 5 times 9.8 meters per second squared. So this is just a little picture to help you kind of understand what's happening. So we have some, the elevator falling some height. It's going to hit a spring. It will compress the spring some amount. I've shown that as x, right? That's our Hooke's law stretch or compression. So again, we're looking at a situation that at different points in time, there's both gravitational potential energy, kinetic, and elastic potential energy. But if we choose specific points, then some of those things may be 0. So I'm going to look first at forces because it mentions acceleration, and acceleration goes with forces. It doesn't go with energies. So I know at the bottom point, again, we have our spring pushing up, gravity pushing down, and set that equal to mass times acceleration. I'm going to solve for the force of the spring. So I just moved force of gravity over to the other side, and then I'm writing in force of gravity I can write as mass times g. So I have big M, which is how it's given in the problem, times g plus big M times our acceleration, which was 5 g's. And so I could rewrite that as 6 mg. The force from the spring, again, comes from kx. So if I want to write that in terms of the compression, so it compresses x amount, and that would be 6 mg over k. I can now use conservation of energy. So we have our initial gravitational potential energy, mgy1, our initial elastic potential energy. There is no initial kinetic energy. We're assuming it's dropping from being at rest. At the end, we have our mgy2, our final gravitational potential energy, and we have our final elastic potential energy. You may have realized while I was doing this that the initial elastic potential energy is just 0 because the spring doesn't start off compressed at all. And it may help us to set our final gravitational potential energy equal to 0. We have to be a little careful. So the amount that the mass falls is not just equal to h, but it's equal to h plus x, right? That's the total distance that it falls. So we have mgy1, which is h plus x, equaling 1/2 kx squared. If I substitute in what I have from above for x for both of those locations, it can look like a messy expression for sure, but you can actually solve it and get a fairly straightforward expression for k. We get 12 mg over h. So this is definitely a difficult, challenging problem, but hopefully you were able to learn a little bit from seeing this solution. All right, our last slide for today is just kind of a summary. There's lots of different forms of energy, and these different forms can transform, right, from one to the other. So you'll often see gravitational potential energy turning into kinetic, turning into elastic potential energy, and so on. And work is done whenever energy is transferred from one object to another.